Hello and welcome back to Data Science Foundations. Today it's another special lesson. We just back to back to back. We're talking about supervised learning, which is really the first time we're going to be talking about machine learning in the context of data science, which might be surprising. Someone might assume that in data science, this would be one of the first or second or third things that you would learn. You just jump right into machine learning. I think you'll see, perhaps not in this lesson, but in the lessons in the future, and you'll see hints in this lesson as to why all that we've learned before is eminently useful, especially in deriving the use and how machine learning should be practiced. So today we're going to be learning about two things. We're going to be sort of defining machine learning, and then we're going to be talking about something which I think is really cool. This is the question, can we actually learn, right? Okay, so let's go ahead and describe machine learning. This is kind of like the heart of the course, so get ready. Probably the next half of these videos are going to be focused on machine learning in some sorts. So we're done. No more hypothesis testing, no more confidence intervals. Not that we didn't need hypothesis testing, but people just use confidence intervals anyway. If you're interested in causal inference or something like that, definitely do check the links above because I've got some videos on that. Okay, so we've got machine learning. You've got a problem. Okay, this machine learning is applied to problems, right? You want to find a solution to these problems, and you need three things about this problem to hold, such that machine learning is the right task. So one, the answer to the problem can't be completely random. So it's not just like you're flipping a coin, or it's not just like you're electing a president, right? Yeah, you just get random results. No, so it's not like there's no pattern at all in the data. And so if there's no pattern at all in the data, for example, you're just looking at random noise from like a satellite or something like that, and there's no actual signal there, you're not going to be able to get any signal, period. The second thing that you need to have is this pattern can't be pinned down mathematically. And you're like, well, that doesn't make sense. Like, maybe you could pin it down mathematically, you could still do machine learning. Well, the problem is you wouldn't want to do machine learning. If you could pin it down mathematically, then you would just pin it down mathematically and do it therefore. There are exceptions to this rule. And so NVIDIA has been producing some papers recently. There's other papers as well. There's complicated formulas and stuff like that. In this case, ray tracing is the one I know specifically. So this is when you've got this scene and you want to make it look beautiful, and so you go ahead and you light it up. And in this case, you need to trace, these rays of light and how they sort of refract and bounce across the scene. But it's very computationally expensive. So actually the true formula, right? But what they've done in this case is they've used machine learning in order to learn an approximation that's really fast. So the second point, a little bit looser, but generally speaking, when you can pin it down mathematically and you can make that mathematical calculation really quick, go ahead and do it. The final thing you need in order to do machine learning, you should all know this already. You need data. So again, you don't necessarily need data right now, but you need to be able to get data somehow. So for example, at my company, we like to do vision tasks, and sometimes we don't necessarily have the data that we need to complete the vision task, so we go out and we gather it. So this can sort of be another important facet of data science and machine learning. How do you gather data that's appropriate to your problem? But we're not going to deal with that. So if these statements are all true, and or the caveats I gave are true, then you can go ahead and do machine learning on your problem. If they're not true, if anyone is not true, you should really think hard about doing machine learning on your problem. If, for example, someone came up to me and they asked me, hey, I've got this problem, and to me it seemed like a problem that could be solved pretty analytically. You don't need to use machine learning in order to do it. And I asked them, hey, what % of the time can you be correct just using sort of this brute force heuristic approach? And they're like 95%. And I'm like, you might want to stick with what you're doing then. Perhaps you can use machine learning to, act on that 5% that you weren't getting. But okay, so now we're ready to do machine learning. Well, fortunately for you, I've gone ahead and I've decomposed the machine learning problem down into a couple of constituent parts. And so the parts are, and let me describe these parts in two ways. I'm going to describe them as sort of foundationally, and I'm going to go ahead and I'm going to describe them in the sense of a loan application. So a very very typical sort of machine learning application that a ton of people still actually do. And it's sort of used as examples in class as a loan application. So you're given this loan application form. It's filled with information on this person. How much money do they make? Where do they live? How much money did they make in the past? Do they rent or do they own? If they own, how much do they own their house? And you want to decide whether you will approve or deny them for a loan. So you're given this loan application. You're trying to decide whether you want to approve or deny them on a loan. So there's lots of parts to this. So one part is the input X. This is the customer application. So it's all the information you know about the customer. The output is going to be binary. It's either approve or deny. That's it. There's going to be something we'll call a target function, okay? And this is the ideal credit approval formula. What this ideal credit approval formula is that it will say yes if I were to have given that person a loan and they would pay it back. And it will say no if I were to give that person a loan and they would not pay it back. So it's as if you were omniscient, right? As if you were the god of loans and you knew everything about loans, right? This would be the ideal function. The target function is what we call. We of course have the data. This is historical records, presumably, of loan approves and denies, and whether they were actually successful. So whether that loan was correct. You gave them a loan, and did they actually pay you back? And then you go ahead and you've got this hypothesis G. So you've got a target function. In this case, this is the real function you want to get. As if you knew everything, this is what you would get. And then you have a hypothesis function G, which is the function that you return back to your boss and say, hey, this is what we're going to use for actually learning. So you return this function and you say, hey, we're going to use this in order to predict, whether this person should be approved or denied. So I'll go ahead and I'll give you a little bit of a visual explanation of this because just listening to me doesn't necessarily cut it. So again, we've got an unknown target function, which is y, f of x in this case. This unknown target function, no one knows it. It could be immeasurably complex. It might give you a little bit of goosebumps though, because this assumes a couple things about the world. One thing, it assumes that the world is completely deterministic, right? So it's an unknown target function. There is some function that's out there that determines, that would determine whether you would, fail or not fail on this loan. So maybe that's not necessarily, it doesn't line up with your free choice worldview and, hey, me too. But so you've got this unknown target function. There's some problems with this and we'll talk about them later. This unknown target function will generate the inputs in the past. So, and this is pretty important. There's an assumption here that you might notice is missing. And that is, where do the inputs come from? Well, they come from the unknown target function, but where else do they come from? So anyways, you've got some inputs, so some X's and some Y's. So in this case, the loan applications and whether they defaulted on their loan or not. And then you do the learning. The learning is composed of these sort of three steps here: a hypothesis set, a learning algorithm, and a final hypothesis. And so basically what you do is you choose a set of hypotheses, so a set of functions that you think the appropriate loan application function should be. The computer learns which function is the best, and it tells you, and then you take that function, you put it back to your boss. Now, you don't need to use a computer for the learning algorithm. Instead, you could choose a couple of functions, and you could test them out by hand, and then you could return the one that's best to your boss. So any of those things will do for machine learning. So now you sort of understand the gist of machine learning. You're basically, in this phrase, the way I'm phrasing machine learning is the functional approximation. So we've got this function. We know a function that takes some loan application to correct prediction, and we want to approximate this function as best as we can. And now other people will describe machine learning in terms of classic frequentists as well as Bayesian statistics. But I'm not going to do that here because no need to complicate things. So we got functional approximations. Now here's the thing. We saw the above, right? We saw the above. Well, hold on. I don't want to spoil anything for you. So we saw the above, and there was an assumption that was missing. And let's make use of this fact that there was an assumption that was missing. Okay. So you should notice by now this missing assumption. I feel like I've got to move myself up so that we can have fun while doing this. But does it matter? Well, the final question, so you know what machine learning is, you know when it should be applied. The final question I have is, can we learn, right? Does machine learning actually work? Is this final hypothesis function ever going to be close to this unknown target function? I don't know, maybe. I don't know. So, can we learn? So using just some data, we learn, so using just some data and some set of hypotheses, we can learn what the true function f is. So suppose we're given this data set. So we see 1, it goes to 1. We see 2, it goes to 2. We see 3, it goes to 3. Okay, so let's use the complicated human instrument called the brain in order to figure out what a good hypothesis would be. And so I asked you, what do you think the true function would spit out, so what the target function would spit out, if I gave you the input 4? Right, and you say, well, totally obvious, 4, right? You know, it's just the identity function. I'm like, wrong. Of course it will be 16. It's obvious. And then I ask you again, well, let's say I gave you 5. What would the true function output if I gave you 5? And you're like, well, I see what you're doing here. This function doesn't really make sense because, you know, some of these things are either quadratic and some of these things are just linear, the identity function, but okay, 25, sure. Wrong. Again, I say it's going to be negative, 743. One final question. Oh, I don't want to spoil it. So the final question is, so what if I gave you 3? What will this function output? And you say, ha, that's a trick. It's probably like 42 or something. And I say, pretty wrong, dude. I mean, you know what the answer is. It's in our data set. 3 goes to 3. So the answer will be 3. You may have caught on to something here. The point is that if you've seen the data point before and you believe in this target function, so you believe it's a deterministic target function, then you can learn. You've seen the data point, you memorize what that data point is, and you spit it back to me. This is kind of like you're writing a dictionary or something like that, or you've seen someone's face before and you write down their name and now you know their name. Otherwise, if you see someone's face, you have no idea what their name could be. The point here is that these points that I've given you, this 1, this 2, this 3, this 4, this 5, these points could be particularly nasty points. They could be points that, were from the tail end of a function that was very complex. They could be points that there was a lot of noise given into these points. These points were given to you by, and I called it Baal, the devil. So someone gave you these points intentionally trying to trick you. Okay, if we can put an assumption on these points, right? Just one assumption. I wonder what it will be. Then we can actually make conclusions about how accurate our hypothesis function will be in accordance to the target function. And so this will be the subject of future lessons. And in fact, this will drive us all the way to the bias variance trade-off, which will be right at the end of class, as well as bagging. Okay, so hopefully that made sense. If you have any questions, please leave them in comments below. If you like my formulation of what machine learning is, in terms of this little diagram, don't worry, there will be more to come. If you have enjoyed the sort of credentials as to what we should do machine learning or when we should do machine learning, you have any input to give, go ahead, please give that input. And of course, feel free to answer the comprehension questions. So if you're new to this, all I want you to do is go ahead and look at these comprehension questions, answer them to yourself, and then if you have an answer that has not been written down in the comments, or you're the first person to comment, go ahead and answer in the comments, and I'll go ahead and check and let you know what I think. So hopefully you've learned what machine learning is, and can we learn? And currently the answer is, it doesn't look like we can learn, Nate. Well, we'll change that next time. Thanks, guys.